Alright guys, so let's move on to do the constraint network just to make our simulation more interesting. Let's actually comment this guy. We can give it a name for exploding force. Have I done that or not? Forget. Exploding force. Okay, so let's move on to the constraint network. This time we're gonna actually let me just drag this down to give me a little bit more force before pack. I'm gonna create the constraint network using the geometries. So we need a connect adjacent pieces. Now this guy is gonna give me a network that is connecting pieces together. The default setting will connect points from one piece to a point of another piece, right? Because that's going to be the connection type here, adjacent pieces from points. Now I'm actually going to use adjacent pieces from surface point. What that does is consider the entire surface, the entire piece as a whole, but it's trying to look for adjacent pieces by looking from the surface of one piece and look towards another surface of the piece. And then see if they are adjacent enough. Okay, so it's more realistic. And what it actually does is scattering a bunch of points, exactly that amount of points, right? And then use that point as reference point to look for points also scattered on other pieces and see if there is a point that is closer enough, smaller than the searching radius, right? If the distance is smaller than that, then let's make a connection, right, from one piece to another piece. And also the connection will be from the center of one piece to the center of another piece. Now 0.1 seems to be pretty good, but if you want it to be higher, you can, right? So you can change that to 0.5 and you get more connections because you're searching basically further. Alright, it's probably searching too far away. I guess 0.1 is good, maybe 0.2, just have a little bit more connection, right? And then we can define like how much search point we're searching for, right? 100 is a lot of points, we don't even need that much. Max connections would be how many connections you want to apply. More means more connections will be added. So if you change that to like 4, you get basically more connections between pieces. Okay. Now I'd like to have a little bit more between the pieces so I can have a lot of connections to hold things together. So and I'll go for maybe 6. It's a little bit more, but you can try different kind of ways. I can go maybe even search a little bit further. Let's try to search 0.5 just to get more pieces involved to others. Cool. Now let's go ahead and do some variations on this constraint network. I'm going to use a VOP for that. So attribute VOP, and here instead of it, I'm working on points, right? Instead of it, I'm going to look for or create a noise, exactly a vor noise, and that's going to be the noise I use to give those guys different colors. I'm going to use the seed being created for every smaller piece that it breaks, right? I'm going to use that to create a random color. Here using 1D integer import and 3D normal, 3D color, right? We connect that to CD. Now we're getting colors. Now the reason I do that on the point level is that that's going to give me solid lines like these and lines that are having 2 different colors. I want those lines that are solid to be solid connections, and line with different colors to be a little bit weaker. Okay, so I can actually do that by using a attribute wrangle. Okay, and here I'm gonna do some coding to get the points. Int point1 will be equals to, if I can make this part bigger. So int point1 will be equals to the vertex point, first input, and prim vertex and also first input, and then add prim num, and then eventually 1, actually 0 for the first one, and then we're gonna copy this guy and then paste it here. So what this does is getting the point number of the 2 points on this line we're iterating through the Rango. Now with those 2 point numbers, we can ask anything about the points. For example, I want to know the color, so vector point, vector point 1 CD will be equals to points, and then we're gonna ask for the first inputs. We're gonna ask for the CD attribute. We're gonna ask point 1 using point 1's number, and we can do the same thing for point 2 CD will be equals to point 0 CD, and then point 2. Right. Now I have the 2 colors. I just need to see if they are the same. So if point 1 CD equals to point 2 CD, then what we do is we give them a stronger constraint name, or a constraint name called glue strong. Strong. And if not, let's actually use color to debug it. So let's also do add CD will be equals to 1 as white color. Let's actually run over primitive. Okay. Now else, I'm going to create the constraint network. Constraint name for these guys will be equals to glue weak, right? And as CD will be equals to 0. Right? With these settings, I'm now being able to do 2 different constraint relationship based on the constraint name. And also, if we can visualize that, I did the color thing is not showing up. The reason being for that is because we haven't really delete the color from the point yet, so they're overriding the color from primitives. So we can do a attribute delete to delete it. Okay, so underneath point attribute, we're gonna select color. Now we're seeing the constraint colors we assign here underneath attribute Rango here, right? So when you see a white line, that means it's glue strong. When you see a black line, that means glue weak. So we have stronger and weaker constraints. So after that, after we have this visual way of representing stuff, we can go inside of the attribute bob. We can grab that var noise and promote, make the mouse click on frequency, promote, right? And then I guess that's it. Let's go up to the top, and we're gonna grab that frequency and change it to make it bigger or smaller depending on how much smaller clusters you want to have, right? The higher this number is, the more smaller cluster you will have, and also the more weak constraint you will have. So maybe I can crank that up just a little bit more, right? So we can have this very interesting web-like constraint network that, again, the black one is weaker and the white one is stronger. Okay. Now one more thing I want to apply here underneath attribute Rango is here I'm gonna give it also a float at break force to be equals to channel. Whoops. Channel break force, and here we're gonna do the same thing for the constraint weak. Oh, let's call this strong break force. And this is right. Now if we run this and click on that add channels, we should be able to see those 2 break forces. Now I want to define how strong a force can break a constraint. That's why I applied or add this attribute. Now this is arbitrary, so Houdini doesn't know what it is, but we can use it later on to actually tell it to break. Anyway, let's just leave them as 0 for now, and we can go ahead and change them later on. So that's basically the constraint network, right? So we're gonna stop right here. In the next one, we're gonna go ahead and apply that in the dot network.